So let's do a summary of everything we have seen so far from both the experiments and the resulting uh, theories that have come out of it. So this is a summary of quantum theory that we've talked about thus far. So the first is that the emission of electromagnetic radiation from matter, so in this case it was discharge tubes of different lights, is quantized, and that delta E is equal to h nu. And this was from the this experiment was the atomic emission spectrum of hydrogen, but we had other ones as well. The second major finding was that electromagnetic radiation has both wave, again not surprising, and particle nature. That was the duality of light. And the resulting theory from that was we're going to put a quantum number, n, in front of this h nu. Or as we put it, so this came from the photoelectric effect. Photoelectric effects, and we got the term photons. I don't know why I'm putting that in quotes. We don't need to put that in quotes. Packets of energy, we put that in quotes, but not photons. And then the next one is that we took this atomic emission spectrum and we were able to describe it using the Bohr's model of the hydrogen atom. Which mathematically described the atomic emission spectrum for hydrogen, and only hydrogen or one electron atoms. And so out of this, so the resulting theory that we had, just so I write that down to be consistent, is that the change in energy for these transitions is Rydberg constant, negative 1.78 times 10 to the positive 18th. No, negative 18th. It's small. Joules, and then 1 over n squared final, minus 1 over n squared initial. That was a resulting theory. So then came de Broglie. That's a D. And de Broglie is a very interesting person. He came and basically said, well, if we showed that light can act like a particle, then why? So if light can act like a particle, or like matter, not like matter, and have particle-like properties, why can't matter? So in this particular instance, electrons have wave-like properties. Now, this is a very kind of groundbreaking and controversial thought at the time. This was not, without experimental data to show this. He was a mathematician, where you had an experimental observation that you couldn't explain. What he's saying is, well, if this can be true, why can't something else be true? And so he very simply said, okay, well, if we have E equals hc over lambda, and he used Albert Einstein's new theory of general relativity, or in the equating energy and mass, then you can simply take the energies, put them equal to each other, and solve for wavelength. So you just combine these two, and you get bring this down a little bit. You get lambda is equal to hc over mc squared. The c's go away, and you get lambda is equal to h over mc. And what de Broglie did is that we're going to change c to v. So this will so apply to particles with velocities less than the speed of light, which is c. We're going to change c to v, so we're going to take that, use that. We're going to say that the de Broglie wavelength is equal to h over m v, where this is the velocity of the particle. This is the mass of the particle. And this is an h is Planck's constant, and the lambda d, the d represents de Broglie's wavelength. Okay. And so this was so controversial that de Broglie presented this as he was a graduate student, presented this as his PhD dissertation in front of a bunch of old white dudes who were coming from a classical physics background. And they heard his dissertation, they heard this radical idea, and they said, you don't pass your dissertation, you don't get a PhD. And so that happens from time to time in grad school. But it turns out that de Broglie was right, and he actually got a Nobel Prize for his work that he defended in his dissertation and was rejected. His committee said, no, that can't be right. And very, very few times has a PhD candidate gone up for their defense, failed it, and then later earned a Nobel or received a Nobel Prize for that work. Maybe this is the only time. But it just goes to show you that the paradigm for the time was very counter to what de Broglie postulated. It was very radical, and he basically could tell his committee, "I told you so." And so yeah, maybe some other things, but he showed them pretty well actually. So anyway, don't let anyone crush your dreams is what I want to say there. So a couple things from this. So basically what this is saying is that any particle that has a mass and a velocity has an associated wavelength. But you might not be able to observe those wavelengths unless the mass is very small. So we can say that the wavelength of macroscopic particles are very, very small. And the main reason is because we have h in numerator, and that's got a times 10 to the negative 34th, okay? And so we have two values. We have velocity, which can't exceed times 10 to the 8th. That's the speed of light. And so the only way to make the wavelength big is to make a mass that's very, very small, so it cancels out here. So you need a mass. So an electron has a mass of times 10 to the negative 31st kilograms. That's an electron. If you were to have something that had a wavelength, so like this is an electron. If you were to have like a baseball that's going to have times 10 to the negative 1 kilograms. So you can see that your wavelength goes to like, it's somewhere times 10 to the negative 25th, which isn't very visible. But if you can see here, if you multiply these exponents, you get something in the nanometer wavelength. So in summary, you have to be very, very small to have a noticeable wavelength, because again, speed doesn't really affect it. It's the size. So if I threw a baseball and I asked you, can you see the wavelength? You would say no, because it's not visible. You cannot detect that. But an electron is so small, it does have, its wavelength is very small. It is meaningful and measurable, and through experiments that have been done. So that means, a lot of talking, but only particles with very small masses will have appreciable de Broglie wavelengths. So, i.e. electrons is the main particle that we're describing using a wavelength. Okay.